We all know that every time you double the CO2 concentration, you get the same additional forcing of about 4 watts per square meter. In other words, the total forcing from carbon dioxide is logarithmic in its concentration. But why does this happen? Well, a popular explanation is that it has to do with the effective emission to space level in the atmosphere. We refer to this as the lapse rate theory, and it works like this. The emission to space effectively happens from some height in the troposphere, let's call it z, and if we double the CO2 concentration, that height moves upward by a fixed amount, delta z. At that new height, it's colder by amount gamma times delta z, where gamma is the lapse rate, and so the rate of emission to space is smaller. And what you get from this is that the total forcing is proportional to gamma, the lapse rate, times the log of the concentration, which we're denoting here by Q. So this is very intuitive, and it's because of that intuitive nature, it's a seductive theory for why it is the forcing from CO2 is logarithmic. Unfortunately, however, it is wrong. And you can show that it's wrong in 100 different ways. And I'm just going to show one of them in particular. Notice that this theory is falsifiable in the sense that it gives the forcing in terms of the lapse rate in the troposphere, gamma. You can check this by taking the troposphere and making it isothermal. What you get is the same logarithmic forcing. So it's wrong. But we can show this in another way too. We can just remove the troposphere altogether, in which case the lapse rate theory has no prediction for what the forcing should be, and yet the logarithmic forcing is retained. And I'll show that quickly here. So here's the logarithmic forcing from carbon dioxide in a standard kind of atmosphere. And you see, well, the x-axis is logarithmic, that's the CO2 concentration. The y-axis is the total forcing, and we see the total forcing marching upwards. For every doubling, we get the same increment of total forcing. This is the log forcing. But we can rerun this calculation by zeroing out the troposphere entirely. Just squash it down so that we have an isothermal stratosphere sitting on top of the surface. And what do we get? Well, we get the same log scaling. And so the lapse rate theory is wrong. It has not even any prediction for what should happen in this particular case. So we're left with the question of what explains the log scaling of CO2's forcing? Well, it has to do with the 15 micron band of CO2, which is the dominant band that is contributing to the forcing from CO2. The 15 micron band has this particular feature, which is that the absorption coefficient has this distribution where it falls away exponentially on either side of the center of that 15 micron band. It is this feature that is so important for understanding the log scaling of CO2. Now, let's think about an atmosphere where I've got a surface behind me here, and we've got a troposphere and then a stratosphere. And I've put a little train track here for illustrative purposes, which we'll understand in just a moment. Most importantly, the z-axis that I've chosen is log of pressure. Now, that particular shape of the absorption coefficient in the 15 micron band, these two exponentials falling away from the center, they imply that the emission to space heights of wave numbers are uniformly distributed on log of pressure. And we can visualize that with a train, where here each train car represents a batch of wave numbers that are emitting to space. Now, a train is a good analogy because a train distributes itself uniformly. You don't have gaps in a train, and you don't have cars side by side in a train. It's just one train car after another. And because this double exponential is telling us that wave numbers emitting to space are distributed uniformly on log pressure, this is an apt analogy. At the surface, of course, there's a solid surface there, so wave numbers that would have emitted from a log pressure higher than the surface pressure are simply emitting from the surface itself. Now, we know that it's warm down at the surface and cold up in the stratosphere, and that means that these different batches of wave numbers are going to emit radiation to space at different rates. And we can visualize that by thinking about them emitting actual just beams of light up to space. The cars at the surface emitting wide, big beams, and the cars up in the stratosphere, thin, narrow beams. So the key message here is that we can visualize CO2's emission to space, and thus its forcing, as this train of wave numbers moving upwards to colder temperatures. Now I want to emphasize that it's very important that we got this double exponential in the 15 micron band. It is the spectrum of CO2 that is so critical. This is what arranges the wave numbers like those train cars. If the spectrum of CO2 were different, if it looked something like this, for example, then we would not get a train. Instead, we'd get this thing with gaps between train cars, and train cars piled up side by side. And there is no train that looks like this. So it's that 15 micron band and its spectrum in particular that's so critical. Well, now that we know that it is arranged like a train like this, we can think about what happens when we double the concentration. Well, when we double the concentration, the train moves forward by one train car. If we double again, it moves forward by another train car. And this is really useful because what it means is that every time we double the CO2 concentration, we are effectively replacing a train car emitting to space from the surface with a train car emitting to space from the stratosphere. We double CO2, and look, we've effectively replaced a train car at the surface with a train car in the stratosphere. We double again, we replace a train car at the surface with a train car in the stratosphere. And this means it's very simple then to calculate the forcing. The forcing from a doubling of CO2 is going to be proportional to, well, the Planck emission difference between the surface and the stratosphere. Here's the expression. Here you see the Planck emission at the surface temperature minus the Planck emission at the stratospheric temperature times this constant pi log of 2 divided by b, which is telling you the size of a train car. And this b is very simple. It's read off from the slopes of these exponentials in the 15 micron band. So we get a very simple story here. And in fact, if we plug in numbers, we find that we get a 4 watt per square meter forcing. Now we've written this up in a paper in the Journal of Climate. This is myself and my two co-authors, Jake Seeley and Jake Edman. This is a very long paper with many figures, but you can skip straight ahead to section 3, which describes the basic mechanism of this logarithmic forcing. And I also invite you to look at some of the earlier papers, and particularly those by Ray in 2010 and 2011, that describe this mechanism for the first time in the literature. And that's why we get the log scaling from CO2. And thanks for listening.